Now let's look at step 2 for the z-test for the population proportion P. Here, we collect our data, check the conditions needed to conduct the test, and summarize the data using a test statistic. We need to collect data from a sample that is representative of the population about which we want to draw conclusions. Generally, the methods we're developing assume that the sample is chosen at random. The randomness is how we're able to apply the results from sampling distributions we developed earlier. Here we're working with hypothesis tests for a population proportion P, so we will collect data on the relevant categorical variable from the individuals in the sample and calculate the sample proportion P hat. This is the natural quantity to calculate when the parameter of interest is P, and now we've learned more about the behavior of this statistic P hat from our discussion of sampling distributions. We will discuss calculating the test statistic as well as the conditions we need to check soon. For now, let's go back to our 3 examples and add this step of calculating P hat to our figures. A machine is known to produce 20% defective products and is therefore sent for repair. After the machine is repaired, 400 products produced by the machine are chosen at random, and 64 of them are found to be defective. Do the data provide enough evidence that the proportion of defective products produced by the machine, P, has been reduced as a result of the repair? The figure displays the information so far and adds the calculation of the sample proportion P hat, which is 64 divided by 400, which is 0.16. There are rumors that students at a certain liberal arts college are more inclined to use drugs than U.S. college students in general. Suppose that in a simple random sample of 100 students from the college, 19 admitted to marijuana use. Do the data provide enough evidence to conclude that the proportion of marijuana users among the students in the college P is higher than the national proportion, which is 0.157? The figure displays the information so far and adds the calculation of the sample proportion P hat, which is 19 divided by 100, or 0.19. In 2003, a poll estimated that 64% of U.S. adults support the death penalty for a person convicted of murder. In a more recent poll, 675 out of 1,000 U.S. adults chosen at random were in favor of the death penalty for convicted murderers. Do the results of this poll provide evidence that the proportion of U.S. adults who support the death penalty for convicted murderers, P, changed between 2003 and the later poll? The figure displays the information so far and adds the calculation of the sample proportion P hat, which is 675 divided by 1,000, which is 0.675. Before moving on, notice that we did not use the information about P hat to help us set up our hypotheses. In practice, the hypotheses are set up before we collect our data. In this course, the data are already provided, which sometimes results in students using the information about P hat to incorrectly help them decide how to set up the hypotheses. We only used information about the overall question to help us set up the hypotheses in step 1. In this case, the question asked if there was a change, with no indication of the direction of the change. Even though our value is higher than the hypothesized value with our estimate of P hat of 0.675, our alternative hypothesis is still not equals. We cannot look only at the difference between the sample proportion P hat and the null value P0 because that would not take the variability of our estimator P hat into account. We know from our study of sampling distributions that this variation, called the standard error of P hat, depends on the sample size. Unfortunately, it depends on the true value of P in the population, which we do not know. In the case of hypothesis testing, since we start by assuming the null hypothesis is true, we use the value of P0 in our standard error equation. We need to do this instead of using P hat, as the p-value is calculated under the null distribution, which assumes P0 is the true value of P. By null distribution, we mean the distribution of the test statistic under the assumption that the null hypothesis is true. The test statistic is a standardized measure of how far the sample proportion p hat is from the null value p0. The value that the null hypothesis claims is the value of p. In other words, since p hat is what the data estimates p to be, the test statistic can be viewed as a standardized measure of the distance between what the data tells us about p and what the null hypothesis claims p to be. Notice that in the numerator, the value from the data comes first, and our hypothesized value comes second. A common error is to swap the values in the numerator, which can cause a serious error in your conclusions. A positive test statistic indicates p hat is above p0, and a negative test statistic indicates p hat is below p0. Let's return to our three examples. In our defective products example, we have p hat equals 0.16 and p0 equals 0.20. Here we've shown the calculation of the null standard error used in the denominator of our z-score. We must substitute the hypothesized value, not the value of p hat from our data. Here we get 0.2 times 1 minus 0.2 divided by 400, and then take the square root. In this case, we get a value of 0.02. To calculate the test statistic in this example, we have z equals, in the numerator, we have 0.16 minus 0.2, which is negative 0.04, and in the denominator, we have the standard error we discussed on the previous slide, which is 0.02. Dividing negative 0.04 by 0.02, we get a test statistic of z equals negative 2. The sample proportion based upon this data is 2 standard errors below the null value. In our survey of college students about marijuana use, we have a p hat of 0.19 and a hypothesized value p0 of 0.157. Here we have the calculation of the test statistic resulting in z equals 0.91. We interpret this to mean that assuming HO is true, the sample proportion p hat of 0.19 is 0.91 standard errors above the null value of 0.157. In our death penalty poll example, we have a p hat of 0.675 and the hypothesized value p0 of 0.64. Our test statistic is z equals 2.31. We interpret this to mean that, assuming HO is true, the sample proportion p hat is 2.31 standard errors above the null value 0.64. We can think about the test statistic as a measure of the evidence in the data against the null hypothesis. The larger the test statistic, the further the data are from HO, and therefore, the more evidence the data provide against HO.